In this hopefully short video, I'll discuss to a general chemistry audience how a particle can acquire a mass through interaction with a field, and essentially we'll finish off this video by having a brief talk about the Higgs field. Okay, so we'll start with giving an example of how a field can generate a mass. Okay, so imagine an electric field. So we have two plates. Let's say we have a positive plate and a negative plate. So we have the electric field going from the positive plate to the negative plate in that direction. So here's our electric field. Okay, and let's say we put test particles in this. Let's do the test particles in red. Let's say now we can have like a test particle. Let's say it's a dipole. We could have that dipole oriented any which way we like, but let's say for argument's sake we have two test dipoles. We have one like this, and then we have a second one that's flipped, so we have the negative here and the positive here. Okay, and we can have everything in between as well. So I'm not saying that these are the only two ways that the dipole can orient, but let's say they're the two that we're comparing. Okay, so if we look at this one on the left, we can say something about its energy. This would have lower energy compared to the other one, and this one would have higher energy compared to the other one. So why are we saying lower and higher? Well, lower energy because it's aligned with the electric field. So we know from just basic Coulomb's law, if this were a static electric field, that opposite charges attract. So we've got this negatively charged plate attracting the positively charged end of this dipole. Likewise, the negative end of the dipole is attracted to the positive plate. So this dipole is exactly where it wants to be. It's behaving itself in the electric field. It's at its rest state, although rest is a loaded word I probably shouldn't use. But it's definitely not in any hurry to rotate. Whereas we look at the higher energy dipole, then we've got repulsion. The negative end of the dipole is repelled by the negative plate here. Likewise, the positive end of the dipole is repelled here. So clearly, I can distinguish between these two orientations in an electric field. Now, we know that energy is proportional to mass. So recall from earlier discussions that energy is proportional to mass. So if I've got a difference in energy, then I've got a difference in mass. So essentially, this is one way to think of, a basic way to think of a field and an object, the field imparting a mass to the object. Okay, so we don't want to talk about electric fields here. Instead, we want to talk eventually about the Higgs boson, or the Higgs field. So we're going to move on from that. Now, you definitely don't need the Higgs field to impart a mass to every particle. So consider, for example, baryons. Remember from a previous video, baryons are collections of 3 quarks. They obey the, they follow, well, they're impacted by the strong force. So we definitely, we don't need to interact with a field just to have a mass. So let's explore this real quick before we get anywhere near the Higgs field. So I'm saying recall, assuming that you're watching these videos in order. If not, you won't recall anything, I guess. So recall the proton. We know that the proton essentially is a bag of quarks. Now it's a bag of quarks. We're going to take the simple view that it's only 3 quarks, although this is an oversimplification. But let's just go with the diagram anyway. So let's say the proton is a bag of 3 quarks, 2 up quarks and a down quark. And it's also got gluons, which I'm going to put like this. So I'm going to acknowledge that this is a slight oversimplification, but it's not useless. But not useless. Okay, so we've got, and for that matter, consider a neutron. Recall the neutron, which again will oversimplify this just to make a point. We have a bag with 2 down quarks and an up quark. Got some gluons. Where here this gluon. Okay, and we know that these objects have mass. In fact, to a chemist, this is where the mass of the atom, in fact, chemists very seldom acknowledge the mass of the electron in regular calculations anyway. You'd have to be doing something pretty unusual to acknowledge the mass of the electron. So we've got this bag of quarks. Now, we're not mentioning any field right now, but let's just consider this bag. So imagine these gluons are springs. I've drawn them deliberately to look like springs, and that's the way people draw them. But you can imagine the up quark pulling on the down quark and the up quark pulling on the up quark if you were to carry this imagery of the gluons as springs. So you would definitely feel something on the end of that gluon. You'd be aware, or there'd be a sense that there's information stuck on the end of that gluon. And just as a real spring, if you really had 3 objects rattling around, so let's see, let's get the black pen. So 3 objects rattling. I don't know if I like that word, rattling. Reminds me of a snake. Do we like tossling? I don't know. We'll try tossling, less snake-like. Tossling on the ends of springs. um, would register an energy change. Okay, so ignore the gluons and the quarks and the neutron and the proton for now. If you just have three objects tossing around at the end of springs, you would definitely describe or know that there is a description there that has a change in energy. And that's kind of what the proton, if we go back now to the real world where we have the proton and the neutron, that's exactly what we have. Details aside, we have objects that can be identified and labeled being held together with forces. We've said previously that the change in energy is proportional to a change in mass. So this tossling around, there's a good chance that tossling's not even a word outside of this video. I haven't had a chance to Google whether that word exists, but that's okay. Tossling, jostling around, tossling quarks and gluons. Would clearly incur a change in energy, and thus would originate a mass. So they would do this because they're composite. That's a good word. So we could say composite, so made of bits and pieces, composite particles such as protons and neutrons have an intrinsic mass independent of a field. Now, obviously, it depends what you mean by a field. You know, you could argue that everything's a field and there are no such things as particles. So how can you possibly be independent of a field? This is the way I want my general chemistry students to think of this. So I'm not looking at any higher level than general chemistry. So a very blunt way of thinking about this. So that's all. Okay, so we have this idea that some composite particles in general are massive. Incidentally, this is why this is one way to think of why the electron is so mass challenged compared to the proton and the neutron, because remember the electron is a lepton. Leptons are not composite. They can't be broken into anything simpler. They're not made of anything. They are things, point particles, without any features. So they wouldn't have this jostling around that would give them an energy and therefore a mass. So they would need to acquire an energy, a mass another way. Okay, so that's a little overview of how you can generate mass from a field. Let's have a quick look now at let's see, I'm going to scroll down here. Let's look at how, so let's go into the Higgs boson. Let's have a look. Or the Higgs field. I think we can just go right there. Keep this video as short as possible. Higgs field. And how, just brief introduction about how this can impart mass to otherwise massless objects. So it's kind of similar, but we'll extend it a bit more, kind of similar to this discussion earlier here about how objects can interact with fields, although we're not going to consider the electric field here. But something related to that. Something related to that. So let's consider we have a particle. So let's say we have a Z0 boson. So this is a weak force carrier from one of my previous videos. And let's say this Z0 boson is otherwise massless, and it has to have a mass, and it's going to acquire mass by interacting with the Higgs field. Okay, so we can have this boson traveling along in, it's moving in this direction, so the motion of the Z0 boson. So this is one of the weak force carriers. It's a boson. So we can imagine the Z boson could spontaneously emit a photon that could terminate. So I guess we could have time going this way. I guess so. The passage of time. So this Z boson is going left to right in time, and we could also later on have out of nowhere, we could have photons unite with the. So basically, what am I trying to say? We can say that the let's see, a conserved property of the Z0 boson is exchanged with a condensate. A condensate, you can imagine, is just a reservoir a never-changing reservoir. So for example, if I give a photon to the condensate, it doesn't have one more than it had before, because that would be to change. This is never changing. If I acquire a photon from the condensate doesn't have one less than it did before. Without going into it in more detail, it's just a never-changing reservoir. It's almost like your parents' credit card balance. You always ask your parents for money, and they always seem to have it, if you're lucky. No matter how much you ask for, it's always like, okay, I've got that, I've got that. So think of it like that. Okay, so we can have interactions that originate or terminate in the condensate. So this could be a termination event. Originate, is that a word? Originate? Origin. Let's go with the origin. So we can originate from the condensate, we can terminate in the condensate. That would be a good way to think of this. Okay. Now it's this interaction. So it would be this interaction. This interaction of the Z0 boson with the condensate, and here the condensate is the Higgs field, imparts a mass to the Z0 boson. It would be this interaction that would impart the mass. Anything else I want to say about that? Yeah, okay. So specifically, let's see. I guess we can leave it at that. I'll get back to my black pen. So this is known as the Braut-Englert Higgs phenomenon. And that's far too many words for most people to remember. So they call it the Higgs, and that's what most people will know it as, the Higgs phenomenon. But these are the three scientists that are attributed to theorizing this explanation of where mass of these particles comes from. Okay, let's scroll down. Okay, so this is theory, and it was theorized, I believe, I could be wrong. I haven't researched the date, but I think it was around the 60s. I think it was somewhere in the 1960s this was theorized. And it wasn't discovered until 2012, and we'll look at that in a second. So let's just comment on the Higgs field versus the Higgs boson. So Higgs field versus the Higgs boson. So a good way to think of it is the Higgs boson, which is the particle, is a compression wave in the Higgs field, which is that condensate we alluded to earlier. So almost think of a slinky to completely lower the tone and look at objects which, a slinky, a spring. So so this would be a compression in our slinky. So we're using an analogy to a slinky. So if two people are holding a slinky, let's say, not to scale, two people are holding a slinky, and person A tries to forces their hand towards person B, and a compression wave is going to travel across the length of the slinky between A and B, then you could imagine that, in general, this would represent the field and the boson. Okay, so we would have this whole thing would be the Higgs field. But this compression wave would be the Higgs boson. Or another way to think of it would be the Higgs field is like an ocean, and a drop of water would be the Higgs boson. Okay. I think that will do us for that. The only other thing to conclude this video, which will probably end up around the half-hour mark, is just some information about what was discovered at the LHC. So again, this is just for a general chemistry audience, specifically my students. Oh, don't want red though. Don't want red. Okay, let's go back to black. So evidence for the Higgs boson and the Higgs field, you can really use them interchangeably. Was found during proton collisions at the LHC, which is the Large Hadron Collider in CERN in Switzerland, I believe. And this was found or reported on July 4th, 2012. And this is all over the internet. You can Google this, and everyone who's got access to a YouTube channel has put something about the Higgs boson. I would definitely, at the end of this video, I'll recommend some resources, some of which were used in me making this quick video for my students, but also that I would recommend, because there's a lot of bogus stuff out there about the Higgs boson. So you definitely want to make sure that you're learning something that is at least reputable enough to be useful, and not so obscure that it's absolutely useless. Okay, so scroll down a bit. Okay, so this is a simplified diagram, but imagine we have a proton moving in that direction, and another proton moving in this direction. Well, the proton, remember from our previous diagram, is a baryon. Now, a baryon is a collection of three quarks held together with gluons. So the proton also has a sea of gluons associated with it. So the proton is just a convenient source of gluons in this diagram. So I'm just going to say convenient source of gluons. A convenient source of gluons. Okay, so we've got our gluons. Here I'll label them G. We've got gluons here. I'll label them G. And these gluons can spontaneously split into a variety of things, but the thing to look out for is when they split up into highly unstable top quarks. So a top quark and an anti-top quark. So this is a top quark T and an anti-top quark T with a line over it. So a particle and an antiparticle. Another way to think of this is if, in reverse, the top quark and the anti-top quark could annihilate each other and produce a gluon again, and energy. So this could happen here. It could also happen here. And you could get a top quark and an anti-top quark. So you can see what's going to happen. We have a collision event that might happen here between a top quark here and an anti-top quark. And if you're just lucky enough, these can meet at this event here. And this would be a likely way to make the Higgs boson. And this is what was discovered with approximately 125 giga electron volts in mass. So proton collisions, bags of gluons, and if you're just lucky enough, then you can see a top quark and an anti-top quark annihilate each other and briefly produce a Higgs boson. So this, I believe, is what was discovered at the LHC. And again, I would encourage you to look into this a bit further if you would like. Definitely resources I've looked at for my own personal exploration of this topic. There's great books. Well, there's lots of great books, but I think some authors that I've read, so I'll put here recommended reading. The reading can be also, audio-visual. There's a lot of audio-visual material online as well. Would be by Sean Carroll. No, I'm totally going to misspell his name now. I think it's double L. I can't remember. And Leonard Susskind. These are two scientists that have a lot of material online, and definitely they both have content related to this this material. So that will conclude. These are, I should probably say, look up. These are the authors of material that will teaching this topic. Okay, so that will conclude this short video for my students at least. Hopefully it was useful to anyone that listens to it.